Okay, let's start. So I'll be standing in for Subhro today and on 8th. And so whatever we will go through in these two classes would be sort of complementary to the regular things that you are learning from Subhro, but I would try to show you another point of view and structure of quantum field theory, which is quite important and interesting, which goes under the name of duality. And I'll show you basically one or two examples of duality. Okay, and then if you're interested, you can just bug me. My office is H207. We can talk about this, or I can tell you how to think about these things more generally. And Subhro, of course, knows a lot of these things, so you can also talk to him. Okay, so just to sort of get the language across again, these two are sort of partly for entertainment, so feel free to ask me questions and stop me, and I'll try to answer as best as I can. So just to make sure that we are speaking the same language, quantum field theory is about trying to understand many degrees of freedom obeying quantum mechanics. Okay, so how laws of quantum mechanics apply to many degrees of freedom which might be interacting with each other, and these degrees of freedom can be very different from each other. Okay, so it could be some of these high energy particles, etc., or electromagnetic fields, both quantum electrodynamics, quantum chromodynamics, and all these things. It could be the space-time itself, if you're trying to understand various features of quantum gravity, or it could be a bunch of electrons or ions which you want to understand as a condensed matter physicist, like I try to do. Okay, so all these class of problems belong to quantum field theory, and we will try to get a point of view from the condensed matter side, which is often called the many body physics. Okay, and this is essentially a different name for quantum field theory, where the degrees of freedom are particular things like electrons, etc. Okay, so let's try to discuss, start with the connection, and gradually move towards this point of duality, which I'll motivate from the point of view of many body physics. Okay, so how should one define quantum field theories? Okay, so how should we define QFTs? So one way to define QFT is to, so we need to specify degrees of freedom. Okay, but how do we go about specifying degrees of freedom? This is turns out to be both intricate as well as at the heart of quantum field theory, how we go about defining degrees of freedom. And then once we know how to define degrees of freedom, then we would like to put some quantum mechanics, like all the uncertainty principle, conjugate operators, etc., etc. Those parts we know. But the question is, how should one go about defining these many body degrees of freedom? Okay, so one way to define many body degrees of freedom is to get this set of the space that you are trying to describe, which contains these many body degrees of freedom, which may be a sort of box of gas, or a box containing electromagnetic radiation, or the star containing quark gluon plasma, whatever it is, into small parts. Okay, so I divide it up. This is a construction. So the end result should not depend upon these things as far as the QFT is concerned. So we define small sub parts of this system. Okay, and let's associate length scale with it. So let's call that length scale A, which is the linear dimension of this small box. Okay, so we introduce a length scale A, which is the smallest length scale of the system, and we would like to try and see how to think about degrees of freedom at this length scale. Okay, so once we define this length scale, we can define Hilbert space associated with each such box. Okay, so basically a set of basic states alpha. So if this is the ith box, alpha I, where alpha runs from 1 to say q. Okay. So I have a quantum mechanics. I am associating a quantum mechanics with this box. Okay. Once I have the basis states, I can write down all kinds of operators in these box. So A, which is basically, I'll use so I can write down all kinds of operators which belong to that box. Okay. So if this is Q, I can write down Q square minus 1 Hermitian operators. Okay, you can check linearly independent. Okay, so if it is a two-level system, Q is equal to 2, the thing that you know, so then for each box, there are two states. Okay, and we can define 3 operators. Okay, so if the matrix form of these operators are in this basis. Okay, so this, as you can as you can immediately realize, are the Pauli matrices which describe a spin half system. Okay, so you just cannot write down any more operators which are linearly independent. You can combine them. Okay, that basically is a statement that if you take a 2 by 2 matrix, you can decompose it in terms of identity and 3 other matrices. Okay, and these 3 other matrices, the identity is a trivial operator. These are the operators that define that act on this Hilbert space. Okay, and then I can do the same thing with each of these cells, and I can get Hilbert space for the entire system. Okay, which is a tensor product Hilbert space for each of these cells. Okay, which basically means that the basis of the entire thing is composed of alpha 1, alpha 2, alpha n, if there are n cells. Okay, so that's one straightforward way of going about defining many body degrees of freedom, many body Hilbert spaces. Okay, and then the operators, you can write operators as, again, product of operators acting on. So whatever operator you can choose AI to be whatever Q square minus 1 at every site, and you get a product of operators. Okay. So that basically defines my many body problem, or in a way you would see the quantum field theory. Okay. So questions? Okay, so this is the length scale at which, so once I define this, my degree of freedom is defined. Okay, I'll more carefully say that the degree of freedom is defined at this length scale. Okay, So this smallest length scale, which right now is ad hoc and is often dictated by experiments at which you want to describe the system, okay, and related things, is the smallest length scale. It has often a name. It's called the UV length scale. Okay, that's basically because the momentum associated with this length scale is very high, and sort of this analogy with optical spectrum, it lies on the ultraviolet side. Okay, so that's the one length scale. The other length scale, obviously, is the system size. Okay, so that's the length scale, that the largest length scale. And since the wavelength associated with this is large, or the wave number associated with this is small, this is called the IR length scale. Okay. So given these two length scales, okay, we can define this thing. So the A length scale defines each of these entries. The L length scale defines how many such entries are there. Okay. And that's it. So once I have this, I can start working. Okay. This is fine. Okay, so let's do this and see how we can proceed. Okay. So often we are interested in continuum limits, which basically means that I am interested in questions where the A goes to 0. Okay. So I have a continuum space, the space in which you do electromagnetism and all these things that from Jackson, okay, you have written differential equations, etc., etc. So you would like to go to a continuum limit. Okay, that's by shrinking A. On the other hand, there is a class of questions where there might be a natural definition of A, like if you define a system on a lattice. Okay. So your degrees of freedom, whatever is defined, for example, on this square grid, okay, you can draw cubic grid or d-dimensional lattices, okay. So the spacing is defined as A. Okay. So this class of problems happen if you want to study quantum field theory, say for crystals, okay, all the spin systems, etc., which gives rise to all these weird phases. So there is a natural cutoff for A, and it does not mean much to talk about distances which are less than A. Okay. But in those cases, the size of the lattice is really large because the number of atoms that makes up this system is of the order of 10 to the power 23. Okay. So if you want to put 10 to the power 23 points, the extent of this lattice is going to be large. Okay. So this goes to infinity. Okay. That's one way to think about this length scale. Okay. And the other way, which is the continuum limit, which is like thinking about taking A to 0. Okay. And both these things gives rise to interesting features in quantum field theory. Okay. What happens is that if you have two length scales A and L, which are very different from each other, you can think about intermediate length scales, small l. And this is the length scale at which you are probing the system, whether your system is space-time itself, whether your system is some quark-gluon plasma, or whatever, you are probing the system at this length scale. You want to understand what are the properties of the system at this length scale, which can vary between this UV length scale and the IR length scale. Okay. And the whole richness of quantum field theory comes in because the description at, depending upon this length scale, this intermediate length scale, the description can change. Okay? And this is the non-trivial part. This is basically new to quantum field theory, does never happen in quantum mechanics. Okay, if you have a particle, whatever the energy scale or length scale you're looking at is the same particle. You can solve the particle for in one eigenstate, and you know you can solve for the spectrum, and you just know everything. Okay. Okay, so this is what we are after, and there are two ways of trying to understand this limit. Okay, so this limit is most well defined when L over A is larger than 1. And remember, always A over L, this big L is always less than 1. Okay. So I want to probe the system at a length scale which is larger than the UV length scale, but much smaller than the IR length scale. So if this is the regime, in fact, most quantum field theories are best described in this regime, which is called the scaling limit. Okay. Now, given the two set of problems that I just said, one of, say, electromagnetic radiation and the other electrons moving on a lattice, on a large lattice, okay, there are two ways of taking the scaling limit. Okay. In case of electromagnetic radiation or continuum space, you take the limit A going to 0 to achieve this entire limit. Okay. So that's called the continuum limit. In the other case, so this is what is done in, say, electromagnetic QED and things like that. In the other case, you take L going to infinity at fixed A. So here A is fixed, L is fixed. Here A is fixed. This is called the thermodynamic limit. And this is often done in StatMech problems and condensed matter. So both these limits recover the same class of quantum field theories in appropriate settings. Okay, it's just the setting, the given problem determines which limit is easier to handle. Okay, and even in QED, you can take the other limit. That's what the lattice gauge theory people do, and you get to answer questions that your standard model is supposed to tell you. Okay. Questions? So that's like the overarching structure of quantum field theory in, like, say, 5 minutes. This class is still 1. Okay. So I'm not going to spend any time on this. This is what Subhro would teach you, mostly this limit, various aspects of continuum quantum field theories. Okay. What I'm going to tell you is that even at the same length scale, quantum field theories may have two different representations. There might be two different actions with completely different set of variables describing the same quantum field theory. Okay? So suppose I have an action where I have fixed my A, L, and small l. Okay? So these are the things that I need to define, and my degrees of freedom are some phi. Okay? This is fine. So Subhro said that he taught you 5-4 field theory, so you can think about this as 5-4 field theory, okay, defined at some Holtzgren length scale with some UV cutoff. Okay. Okay. So it turns out that there might be a completely different description at the same length scale of a completely different set of fields, okay. For every correlation function I can calculate here, there is a corresponding correlation function here, okay. There is a one-to-one mapping of correlation functions and observables, even though the structure of these quantum field theories may be quite different, okay. So we would like to understand such relations in simple examples, okay. So these, the most famous of these connections are called dualities, okay. So if we go a long time, which we don't have to, then by the end of second lecture, by the way, second lecture is on 8th, if I haven't said. So I need to travel on 10th. So I'll take the second lecture on 8th. That was not decided. And if there is need, we can have more classes. We can discuss that with Subrat. Okay. Okay, so if it goes well, I'll show you that a system of bosons, okay, in 2+1 dimension is dual to a system of electromagnetism. Okay, so this goes under the name of various names: particle vortex dualities, boson vortex dualities, abelian Higgs duality, and various kinds of things. But essentially, the point is again, there are many other examples. Two different, apparently different looking actions can describe the same quantum field theory. Okay, so this is what we are after. Okay, questions? So sometimes this connection is helpful. Okay, suppose you want to calculate some correlator in this action, but you don't know. If you try to draw Feynman diagrams, so you have started diagrammatics, right? If you try to draw Feynman diagrams, you would see that the number of relevant diagrams is like huge. Okay, so you cannot do it. Humankind don't know how to do it. Okay, so on the other hand, the correlator that has an equivalence here may be obtained by doing one diagram. Okay, so then that's like fantastic. Okay, sometimes they are just gives you more mathematical insight. Calculating the correlator is difficult in either of the pictures, so it is not as helpful, but it gives you certain idea of the mathematical structure of the quantum field theory. Okay, so in other words, sometimes it's useless, sometimes it's useful for practical purposes, but of course, this is a structure that is very nice, and it would be useful to understand that. Okay. Okay, so let's start with the simplest of the lot. Okay, let's start with this Hilbert space that I had defined at every site. So since I'm a condensed matter physicist, I'll think about thermodynamic limits and lattices. The good thing is that I would be able to do all integrals in real time, and I don't have to think about measures which might blow up, etc., even though one can do it in that language also. Okay? Okay. So let's start with defining my system. Okay? So the system is a 2D lattice, like a square lattice or something simple like that. And at every site of the lattice, there are two states. Okay, so this at every site, or you can label them up or down. Okay, 1, -1, whatever. Okay, so it's a spin half system. Okay, by the way, I won't go too much into the discussion of symmetries. Okay, I have a lot to say about symmetries in quantum field theories and things like that. We are having a different course for that right now. But if there are questions, I can try to answer. Okay. Okay. So so at every site of this lattice, there are these spins, and I can write down the SZ, which is in this language, this in this basis, this is this, and Sx, which is 0, 1, 1, 0, and Sy, which is 0 minus I, 0. Okay. You can write down the operator forms of this, but this is my these are my operators. Okay. Okay. So let me immediately write down first the Hamiltonian and then the action. Okay. So the Hamiltonian of this system is minus Szy, Szj, Ij, nearest neighbor, minus gamma. How many of you have seen this? This is often the 0th problem that you study in StatMech. This is called the Ising model. So everyone has seen this in StatMech. Okay, maybe not this term. Okay, but the first term. Okay. So you know that this has a phase transition at high temperatures, average value. So if you decrease temperature, okay, so temperature, so without this term, temperature, you at high temperature, average value of Sz is 0, and here the average value of Sz is non-zero. So it undergoes a ferromagnetic transition. Okay, at gamma equal to 0. That's the kind of things that you must have learned. Okay. Okay. So suppose you are at t equal to 0. Okay. So this was gamma equal to 0. Okay. Suppose you are at t equal to 0. Let's keep only the gamma positive side. Okay. T equal to 0 and change gamma. Okay. So what happens? Okay. Let's think about the gamma equal to infinity point. Okay. So at gamma equal to infinity point, you can basically neglect this part. Okay. So here, the ground state is all the spins pointing along the x direction. So all the spins point along the x direction. And that's the ground state. Okay. Fine. So that's the ground state here. So whereas here the ground state is everything in the z direction, or the z, I don't have a level, all up or all down. Here. So that's the Z2 symmetry broken state. Okay. So sitting here on this line, as you turn on gamma, there is another phase transition here where the Z2 symmetry is restored. Okay, and one can try to draw the entire phase boundary in this gamma t plane. This is what is called a quantum phase transition, okay, happening at t equal to 0. Okay. So one can think about writing down Landau-Ginzburg theories for that quantum phase transition, etc., etc., and one can study all these things. And that, in fact, this is the famous Onsager exactly solvable point. Okay. No, the quantum phase transition is strictly defined at 0 temperature. You can ask, what is the effect of this quantum phase transition at finite temperature? That's what we really are interested in, because it's impossible to access this point. Okay, we cannot cool to 0 temperatures. Okay, it's just a theorist construct. What really happens is that we are interested in the property in this region. We can ask, what is the influence of the physics, this physics, of this point? Okay. Okay. So again, one can study phase diagram of this model, but that's also not what we are going to do. Okay. What we are going to do is to say that we would write down the action for this Hamiltonian, okay, and we will say that there is a completely different action, okay, which describes the same system, okay, and we'll work out this transformation, okay. And what would happen? So this, in my case, is the Ising model, okay. It would turn out that in this case, the model which describes the same thing is a model of electromagnetism for Ising's gauge. Ising electromagnetism. Okay, we'll see what Ising electromagnetism means. But you would see that this basically has the same structure as the Jackson theory that you have learned. It would have an electric field, it would have a magnetic field appropriately defined for the Ising regime, okay, Ising spins, okay, and the action would be of the order of E square minus B square. Okay. So of course, not the kind of action that you have seen in Jackson, but because it's an Ising system. But once we go on to bosonic systems, we'll see this. So we'll work out the details of how to go from this to this. Often, this kind of transformation starting from one to the other is very, we don't know many of examples. So this would provide a rare instance where we can start from one field theory, a lattice field theory, and go to define its dual description. Okay. And so it's the same degree of set of degrees of freedom. It just have two descriptions. Okay. So I don't know what you mean by fundamental. It's you see that these are quantum degrees of freedom. Okay. There are many ways to partition the Hilbert space. Okay. So you could have asked that. Instead of doing that kind of cell division, I could have done a cell division where the cells are sort of 1D. Okay, so I have my system. I just split them up like this. That's the first cell. That's the second cell. That's the third cell. Okay, this is my construct. Okay, so of course the degrees of freedom, okay, in which I want to define, with which I want to work, does not depend upon this construct. Okay, it's either given by somewhere else, like the problem is naturally defined on in some cell, or in other cases like electromagnetism, you want to define the electric field locally. So so we have a preconceived notion of how to think about quantum field theory. But the quantum field theory does not care about that, right? When you try to define electromagnetic field, okay, and quantize it, you would like to have a local electric field at every point, okay? But that mostly comes from the fact that you had differential equation at the classical level, the Maxwell's equation, and that's where this idea of local field came from. Okay, but once you quantize, the quantum field theory might have the same the local field might have a completely different representation in some other basis. Okay, so the question is that are there nicer representations, other representations of quantum field theories? Okay, so you could ask even more simpler question. Are there can a quantum field theory have representations where there are no classical, no local Hilbert spaces like this? Okay, that's a valid question. Okay, we know of examples like that. Okay, so you cannot write down particle-like description. So when you have a local description, it means that it has a particle-like description. Okay, so we can write down those particle-like descriptions, but that does not work. Okay, so this idea that quantum field theory might have different representations is basically tied to the fact that you have the many-body Hilbert space. How are you representing that many-body Hilbert space? Okay, and it does not have to be local. We would like it to be local, okay, because then we can use a lot of different kinds of mathematics, etc. All these tensor product structure, etc. uses that locality ideas in one way or the other. But you can calculate entanglement and things like that. Okay, but the quantum field theory doesn't care, right? Huh? Sorry, I didn't. So when I write down the quantum field, what I mean by local, say for example, this is what you learned. Something so each of these fields is a local field, right? So if I quantize this, if this was not there, I could quantize it exactly, and this would give rise to particles, okay, which you can form wave packet and study their quantum mechanics, okay. So actually, if you take this term and sort of fine tune some of these things, go to what are called Wilson-Fisher fixed points, you see that there are no particles. Okay? So that's signaled by the phi-phi correlator having structures. This kind of correlator. So in absence of the U term, this would have the structure in real space. So let me write down k omega minus k minus omega. This would have a structure which is omega square minus k square minus r. Okay? So you can use a pole to define a particle. Okay, you would lose that pole. There would be branch cuts and things like that. Okay, so then you cannot define particles. Okay, you can ask, are there representations where you can still get away by defining poles? It doesn't look like. Huh? Yeah, so the same length scale is very important because for the kind of dualities we are going to talk about, they're important because I would like to define the dual theory on something similar picture. Okay, it's not essential, but it's a subset of the relations that we would like to work on. Okay. I think we don't know the answer for, carefully, okay, but there are some indications that it might. Okay. Yeah, all these are very important questions. So, more questions? Okay, so let's go on to the technical details. So from here on, the rest of today's class and maybe the next one, I'll start with the action corresponding to this and derive the dual theory. And in the end, we will see that it's secretly a theory of electromagnetism. Okay? Questions? So you are familiar with deriving the path integral from Hamiltonian? Huh? This is fine. So suppose I try to write down, I try to calculate that's the Hamiltonian. I want to calculate the partition function, which is trace of e to the power minus beta h. Okay. Okay. I'll tell you a statement and then tell me if you're familiar with this. This is equivalent to imaginary time path integral. This okay? No, just tell me, otherwise I'll lose you. Okay? Is not okay? Okay. So the evolution operator. So this and this form are identical. Okay. So basically, you can define your complex time. Okay, let's call whatever t tilde. Okay, this is your real time, and this is your imaginary time. Okay, tau. Okay. So you're interested in trying to understand the theory in this direction. Sometimes in this direction, if you're thinking about thermodynamics, okay, or statistical mechanics. Okay, generically, you can rotate a field theory. You can study the field theory in the complex plane and either rotate from the real to imaginary or the other way around. Okay, and that's how these two things are related. Okay, so this, if you try to write down partition, so you know how to write down partition functions using this. So the way to go about is that if you have an amplitude like this, or really this, f, okay, you write u of t as product of epsilon going from 1 to n, u of epsilon. Okay. And then introduce identity, a set of all states, okay, basis at each of these, and then you try to define the path integral. Okay, this thing is clear. Okay, you can do the same thing here. The only difference is that I is equal to f, and that's summed over. Okay, so you would get a field theory here, which is in the imaginary time. Okay, where here the epsilon ran from 0 to t. The here the epsilon would run from 0 to beta. Okay. So these would give you path integrals in imaginary time. Okay. So the point is that if you do an exact calculation here, okay, often this is easier because this I is not there, which leads to more convergent integrals. Okay. So this claim is that if you know everything along this line using analytic continuation, you would be able to transfer all the results on the real line. Okay. But that's like mostly very statement of principle, because even along this line, you don't know how to solve it exactly. Okay, so you only know approximate solutions along this line, and then the analytic continuation is not very very easy. Okay, so there are tricks to do these things, which one is typically taught in. So I think if Subhro teaches finite temperature field theory, he would touch on this, or you can take a many body course to learn everything about this class of problems. Okay, but let me try to focus on this issue. and try to derive the path integral for you. Okay. Okay. So this is equal to summation. I'll take the SZ basis. Okay. SZ Is this fine with you? So this curly bracket means that SZ for all the spins. Okay. Okay. I'll now do the splitting. Okay. So for the splitting, so to do the splitting, I'll keep on getting summations, right? So let me try to do this more carefully. Again, I don't want to do things that you know, but I don't want you to miss out on important things because these are useful constructions. So just tell me if you're familiar with these things, all of you, or most of you, or whatever. Do you know how? Let me write down the answer, and then maybe you can tell me if you know this. That the action corresponding to that Hamiltonian, H, as I have written, the action corresponding to that Hamiltonian is J I J S Z I S Z J, where I and J, so this small I and small j was really a two-dimensional vector. So the small I was really Ix and Iy, specifying the coordinates of this square lattice. Okay. So, but this I and j is I and a time direction tau, which goes from. So basically, the construction is like this. So this was my square lattice that I was drawing. Okay. And then there are such slices of square lattice. Okay. This at tau equal to 0, tau equal to 1, all the way to tau equal to beta. And I can draw. So this is, say, I, this is I, and then there is a link which is between the same space points but in the time-like direction. Okay. So the action that I wrote down is equivalent to Ising model, the classical Ising model, in one higher dimension. So if I draw all these links, it would form this cubic lattice. Okay. So at every point, I have the square lattice. At every slice, I have the square lattice. And this is the description in terms of path integral. At every point, at every time slice, you have your Hamiltonian, but then it covers the entire time evolution. Okay, just like wall lines and things like that, you might know. Okay, is this familiar? If this is familiar, then I won't derive. Okay, this is important, but should I not? What's the vote? Okay, good. So let's try to do this. Okay. So let's write beta as epsilon into n. Okay. Or yeah, so epsilon into n or tau into n. Okay, let's keep epsilon into n. I'll see what like okay. Where n goes to infinity and epsilon goes to 0 gives us the continuum limit. Okay. Okay. So then I can write this down as tau running from 1 to n e to the power minus tau h. Okay. I'll try to keep as much detail as possible. So then the identity that we require is summed over all SZ is an identity, right? Okay. I'll insert the identity. I'll write up the product. I'll insert this identity at every point. Okay. Fine. There is a similar identity in the X basis. Okay. So fine.
Hello.
Are there people online? Yes.
Sir, can you explain the thing you
Just hold on. This voice, this sound. Yeah.
Can you explain the grid that you drawn for describing I, capital I and capital J on RHS? I did not understand that.
Oh, did you understand the small I and small j?
Actually, the index I was not able to get what it does they mean.
Yeah, so this goes back to the picture that I have now erased. Okay. So I had this. So you can see this square lattice. You can see this?
Yes, sir.
Okay. So I and j were points on the square lattice. Okay. The small i's. Okay.
Okay.
So to define points on a square lattice, okay, we know these distances are a, okay, and these distances are also a. So any point on the square lattice R, okay, or I, which is what I was denoting, is some number, some integer into xa into x hat plus some number, some other number into a into y hat. These are integers, okay? So I am denoting those integers as ix and iy. This you agree?
Yes.
Okay. So this was this notion that ix is really a two-component vector denoted by two integers ix. So I is a two-component vector with two indices which are integers ix and iy. Okay?
Yeah.
Okay. So you would soon see that once I try to do this, so because I'm doing this time slicing, I'll gain another direction, which is the time-like direction, which is why your actions are also integrated over time. Okay. So I would need to talk about a third direction, which sort of is the time-like direction coming out of this board. Okay. So I would, in some sense, need three indices. Here I had two indices. I would need three indices. Okay, that's what I have tried to define using the uppercase I and j. But if you are, so I'll come back to that notation. That was just to tell you where we are going, but it's okay if you didn't get that notation. But the spirit is that if I try to write down an integral, there would be a time-like direction, the action, there would be a time-like direction, and I would need a third index to specify both the two for the spatial part and one for the temporal part. Okay, that's why I would need three indices. So I tau is basically gives me three indices. Okay, we'll come to that more explicitly. But at this point, you should be sure that you are comfortable with this fact that I need two indices to specify my Hamiltonian.
So actually, it's like two-dimensional space and one-dimensional time.
Yeah.
Okay.
Okay. Yeah. Okay. Are other questions related to this? Okay. Okay, so here, so let's start with this. Okay. Okay. So let me write down a few things. So at every point, I'll insert the first identity in the Z basis. Okay. So I'll get the following thing. Are you comfortable with this? I have inserted this identity here. Okay. And this is a sum. Okay. I'll now insert an identity here. So that's this. There is a sum over tau. Okay. So these numbers denote that, huh? Why? Huh? All these intervals that I have split, I have, so 0 to beta, I have split them in equal intervals, tau, which are small intervals. Okay. Sorry, I think I denoted them as epsilon. Ah, thanks. Yeah. Okay. Sorry. Is this fine? So if I write this down, okay, you would continue this. So if I write this down, I'll get summation over SG. This was my original SG that was present. Then I would have SZ the first all the way to SZ nth, the nth resolution of identity before here, okay, and then SZ E epsilon H SZ1 into SZ1 minus epsilon H SZ2 all the way, and the last one would be SZN minus epsilon H. Sorry for going here. We won't be able to see that. Is this fine? Okay. Now I'll just make one notational change. The original SZ, yeah, you see that if I just put a subscript on this as 0, okay, then you see that it just ties well with the subscript that I'm going in this direction and coming back, the periodic direction. So S0, S1, S1, S2, S2, S3, S4, S5, all the way up to Sn minus 1, Sn, Sn, and then S0. Okay, so I'm sort of having a periodic boundary condition, which is what was guaranteed by the trace. Okay, so it's just for optics. Okay, fine. Okay, so what I really have to do is to calculate this object. Okay, is this fine? So let's calculate one such time slice, and then we will be done. So a typical time slice looks as follows. Okay, S Z. Okay, something say tau e to the power minus beta h sz tau minus 1. Okay, two different things differing by 1. Okay, okay, I want to calculate this for h equal to whatever I wrote, SG, SZ, IJ, IJ being nearest neighbor, okay, minus gamma, SG, SX, I. Okay. Now, again, if gamma was 0, this is easy. Okay, because I have written it in SZ basis, and what happens here is an eigenstate of SZ, these terms, so it's done. Okay, so this is easy. The thing that makes it complicated is this term. Okay, and in fact, this term is what makes the problem quantum. Okay, if I had only this term, none of the operators inside the Hamiltonian have any non-trivial commutation. So all terms commute with each other. So I could replace them with their eigenvalues, okay, without any conflict. Okay, so that's the classical problem. If you trade in all the operators with their eigenvalues, and you end up with, if you can do that, you have a classical problem, right? It's because of this, that this part of the Hamiltonian does not commute with this part of the Hamiltonian, we really have quantum mechanics. Okay? Okay. So then let's try to understand this. And so this is equal to, suppose I act on this side, okay, e to the power minus epsilon summation over I S Z I tau S Z J tau. Okay, so this says that I have acted this part on this basis, and whatever the basis value of this is, that eigenvalue is picked up by this term. Okay, is this clear for the first term? Then I have epsilon gamma summation over I S I X. Okay, S I X. This is what we need to calculate. Okay. How should we calculate this? So the easiest way is to introduce here this identity resolution in terms of Sx basis. Okay. So just this part I'll write as Sz tau. I'm doing it here, so it doesn't matter. You could do it here. At the end, it doesn't matter. Okay, so yeah, sorry. Since I have not done this calculation in a while, there would be lots of mistakes. So just point them out. Okay, I'll try to minimize them. Now I know how to calculate this. Okay, this is equal to, but the cost of doing this is that I have to now tell you what this object is. Okay, okay, so this is equal to Sx tau S zeta. But do you see a familiarity with this matrix element? If you were doing it for a single particle, okay, there was p square plus v term in the Hamiltonian, you would introduce x basis. This would be diagonal, but this won't be diagonal. Okay, then you would introduce a p basis and you would get these terms. Okay, those are exactly these things. So the structure is extremely general. Okay, that comes from the non-commutativity. Okay, and that's where all the operator relations are hidden in the path integral. Okay. This is e to the power minus epsilon gamma summation over I Sxi tau. So this says that this is like the eigenvalue of this. Okay. Tau minus 1, a different index. Okay. This is again very similar. So x tau, xt, tt into x into pt into x t minus 1. This is the kind of things that you would get. So this would give you e to the power I t x pt into xt, and this would give you e to the power minus I pt into xt minus 1, and that together would give you e to the power I pt into x dot of t into delta t. Right? So we need to find out analogous relations for that. Okay, it's fine. So what is this object? Okay, so let's go back to the connection that it is. So remember, up of x is equal to, in terms of z, and down of x is equal to up. Okay. So what you are trying to understand is what are these relations? Up x, down, this is z. Okay, up x, up, down x, down, down x, up. Those are the four matrix elements you want to calculate. Okay, so let's see what this is. Okay, so what is this? 1. Okay, what is this? So really 1 over square root 2. Okay, but 1 over square root 2, 1 over square root 2. What about this? This is the form. Okay. Okay. Let's try to write down an operator form for this result. Okay. So this would be analogous of e to the power itx, right? Okay. So I think that let's try. I've forgotten. I think this works. Let me try to check. So up, down. Yeah. Check. So this term only fires when both of them are down. Okay. So this is 2, this is 2, that kills this 4, I get t to the power I pi minus 1. Otherwise, if any of them is up, this exponent doesn't fire, so it's e to the power 0, so it's 1. Okay. So that's the operator, that's a functional form of these matrix elements. Okay. I've just, it seems that I pulled it out of the hat just because I have known this for a few years. Okay, but once you look at these kind of things carefully, it's basically the same as calculating this object. Okay, so remember how you got to that basis. It's actually much easier than that. Okay, so with this, I would now need to go back to the single matrix element and try to do. Okay. Remember, we are calculating one of these matrix elements, and that we are here. Okay, so let's, yeah, those are just eigenvalues. Okay, yeah, so those are either +1, -1 type of things, and I've thrown away this. This gives us overall constant. So, yes. Okay, so what is this? This is equal to S. So I'll also write down this previous thing so that in case I erase it, this SZ term. Okay, so this entire matrix element is minus epsilon summation ij sci tau scj tau. Now I have this piece summation over sx tau e to the power minus gamma epsilon gamma summation over I sxi, and then I have this piece and this piece. Okay, so for this piece, the first piece, I have e to the power. So there would be 1 for every I, okay, for every site. So there would be a sum over I, and then that is I pi by 4, 1 minus si x tau, 1 minus sz tau. Okay, that's for this piece. Okay. Both the indices are at tau. Okay, and the psi came from the fact that there were, like, this was really this s I equal to 1 z, so all the i's were present. That's its curly bracket. The other thing, e to the power minus I pi by 4, summation over I 1 minus Sx I tau minus 1. Sorry, tau. Sx is still a tau. 1 minus Sz I tau minus 1. Okay. It's conjugate xz and not zx. Fine. This is equal to what? I've just taken. So I also have this term. So this is, I now need to try and understand what this term is. Okay. Okay, let's try to do this. So what I'll do is that I'll add and subtract 1 to put it in the same form as this. Okay. So there is a constant which I won't care to write. So take this 1 and I'll write it as 1 minus Sx tau. So you see what I've done. I've just added this. I've taken the minus sign inside. I've just added this 1, but that's just a constant. Okay. So I can then write this piece as summation over Sx tau e to the power summation over I 1 minus Sx I tau into epsilon gamma plus I pi by 4 Sx Sz I tau. So, I would do one more thing. I'll just rearrange things. Okay. So what I'll do is that I'll take out a 2 because I want this to be 0 or 1. So this is just, this term is there, but this is what this term boils down to. Okay. Now you see an important feature that this entire thing is diagonal in this index I, the site index. So I can do this sum at every site independently. Okay. So I can rewrite this part as product over I, okay, sum over Sxi tau, okay, equal to plus 1 and minus 1 e to the power 1 minus Sxi tau by 2 into this thing that I have written here. So this entire thing inside, I've been able to do this. I can do this at every I and then take their product, which is the tensor product. Okay. Okay, what is this? So this sum I can do. So you see that, so all these things are sort of gradually trying to simplify the problem to a point where I can actually do summations. Okay, this sum just involves two terms, so I can just do it. Okay, so what are the two terms? So when Sx equal to +1, so you see that whatever is in that square bracket does not matter because the thing vanishes. Okay, so that term product over I, that's equal to 1 when that's when Sx is equal to +1, and then when Sx is equal to -1, then that prefactor is just 1. What survives is that e to the power twice epsilon gamma plus I pi by 2 s z I tau minus s z I tau minus 1. Okay, that final piece, this one. Okay, so I have gotten rid of one sum, the Sx sum. Okay, there are sums like this Sz sum sitting outside. Okay, now, okay. But okay, fine. Everyone with me? Okay, I'll now rewrite things. So we are almost done. Okay, okay. So I'll rewrite e to the power twice epsilon gamma as tan hyperbolic j tau. Okay, that's the definition of j tau. Okay, you would soon see why this redefining things is useful. Okay, I'll just okay. So that's the definition of j tau. Okay, through this point. So then I can rewrite this object as I. So this is equal to cos hyperbolic. Okay, should I do this? Yeah, sorry, sine hyperbolic. Yeah, j tau and cos hyperbolic j tau. Okay, so I can write it as cos hyperbolic j tau. Okay. Okay. For this part. What about this part? What is this? Let's see. When both of them are +1, okay, this object is what? So I'm thinking about this part. This is easy to calculate. Okay, both of them are +1. This is 1. Agreed? Again, it's sort of similar to this. Okay, one of them is +1 and one of them is -1. -1. Okay, in both the cases, both of them are -1. It's again +1. Okay, so this is actually, convince yourself, this is actually equal to SI It's just a fancy way of writing this. Okay. So if I try to write this, agreed? Okay. What is this? This I don't care. This is constant. I mean, beta, epsilon, these are just measures. Should I this? Okay, anyway. What is this? Okay. So remember, this can be either +1 or -1. Okay. If this is +1, okay, I have cos hyperbolic plus sine hyperbolic. Okay. So that's e to the power j tau, because cos hyperbolic j tau is e to the power j tau plus e to the power minus j tau, and sine hyperbolic, I don't care about factors of 2, minus e to the power minus j tau. Okay, so if you add cos and sine, this part survives. So it's 2 into e to the power j tau. So if this is +1, so both of them are +1 or both of them are -1, then this gives cos plus sine hyperbolic, which is this part. If this is -1, then this and this cancels, this becomes plus, I get j to the power minus. So this is actually equal to product over I e to the power j tau into sz I tau sz I tau minus 1. Okay, this thing inside this square bracket. Okay, so you put both of them up or both of them down. Okay, you get j tau again up to factors of 2, what not. Okay, I don't care. Okay, fine. So we are finally done. So this sliced object, okay, this single time slice is equal to, so that thing, okay, is equal to e to the power minus epsilon summation over ij sz I tau sz I j tau. Okay, that's the first piece. And I can now convert this product into a sum for the, okay, this is equal to e to the power summation I j tau sz I tau sz I tau minus 1. Okay, and then this is equal to minus summation over I what j tau s sc so it should be +1. Okay, fine. What I tau tau minus 1. Okay. Actually, I think now I have made a sign error with this term because I started out with the Hamiltonian h is equal to minus sz sz. Okay, so when I put this sign should be plus. Okay, I didn't notice that. Sorry about that. Just go back and check that there was a sign error because of this extra minus sign, which I didn't take care when I wrote down the SZSZ part. So this sign should be plus. Sorry about that. Check. Okay. Okay. So now I can go back to my path integral, okay, with all these things. Let's do that. Oh, V. Perfect. So let's now add. So this is where we started from. Okay. And this is where we are. SZ0, SZN. Okay. So those were the initial summation. And for each of these slices, I have e to the power epsilon, okay, into Sz I tau, Sz j tau, okay, plus summation over I S j tau, Sz I tau, Sz I tau minus 1. Okay. So now let's go back to this uppercase indices. Okay. So each of these things, and there was a question online. Sorry, I don't know who you are, but so this is coming back to your point if you're still around. Okay. So this is really a summation. So how does this summation look like? Okay, or any summation in between, say SZ tau look like? Okay, so this looks like as follows. Okay, SZ of I equal to 1 tau. This only this summation. Okay, SZ of I equal to 2 tau plus minus 1 plus minus 1, all of them. So this summation is really n summation, where n is the number of spins. Okay, that's what this curly bracket meant. Okay. Now, similarly, if I expand this summation, it would be the I index won't change. It's just that the t index, tau index is at 0. Okay. Here, the tau index is at 10. There are still the I index doesn't change. There are as many. So if I really think about this is equivalent to a summation of SZ, okay, I say I equal to 1, tau equal to 1 to SZ I equal to some n spin, tau equal to beta. Okay, so this huge set of summation. Okay, I can at site I have a summation over tau 1, 2, 3, 4, 5, 6 all the way up to beta. Okay, so let's club the summation. So then final summation SZ I equal to 1, tau equal to beta. Okay, and similarly at every site. So you see that this is equivalent to saying that I have a 3-site index. These were two indices. I was 2 indices, Ix, Iy. Now I have a third index, tau. So Ix and Iy go over the number of sites, and tau go from 1 to beta. Okay, and then there is a periodicity because S0, it's a trace. Okay, so that I can incorporate by saying that there is a 3-dimensional, this is the picture that I was drawing. So this is the tau direction. this is 0, this is beta. Okay, at every tau, there is a square lattice, okay, whose indices are I, the small I, the old I. So if I combine this I with the tau's index, I get this uppercase index. Okay, so I can sit at the same site, I can go in the tau direction. Okay, that's this third index. I can sit at the same tau and go in the plane. Those are the first two indices. Okay, and then there is a periodic boundary condition in this direction because of this trace, which is the first term is equal to the last term. Okay, fine. Let me know if there are questions if this doesn't resolve. Okay, so with those things, I'll just write down the final answer and we'll get back to this, starting with this. So Z is equal to S, okay, Z. Now this sum, okay, I'll write down a double bracket. This involves the sum over the uppercase I index, which is like the shorthand form of this entire thing. Okay, what about this? Okay, so for every such thing, there was a summation. So for every such every such slice, there was a summation in the coupling tau and tau minus 1 or tau plus 1. Okay, so if I combine all those summation, there is a summation over tau here. Okay, so I'll write down e to the power minus s, and I'll write down s. So this is script s. Okay, this is the action. Okay, I'll now write down the action, which we can now discuss. Okay. S, since I have pulled out this minus sign, S is equal to minus summation over tau summation over ij being nearest neighbor epsilon sz I tau, okay, sz j tau, okay, and then the second term, again, since I pulled out a minus sign, is minus summation over tau summation over I j tau sz I tau sz I tau minus 1. Okay. So let's look at the first term. The first term, sorry, why did I erase this slicing? Okay. What should I erase? Let me erase this thing. Okay. So the first term is sitting at the same slice, okay, coupling two neighboring spins with this coupling constant. Okay, so this term is at the same time slice tau, coupling two neighboring spins. If this is I, this is j. Okay, j could be any of these neighbors, but okay, that's the first term. What is the second term? The second term is sitting at every I. Okay, sorry, so this is I, this is tau minus 1, tau minus 1, okay. The coupling is between the same space-like site, but between two neighboring time slices. If there is tau and tau minus 1, there is also tau plus 1 and tau, and so on and so forth. There is a sum over tau, okay. So it's coupling along these directions. So there is also a coupling in this direction, so at every site, okay. So, and they couple with this amplitude j tau, okay. So all together, I can write down this in a more compact form. S and this is what I was writing down, summation over ij nearest neighbor, okay, minus jij, because in some direction it's epsilon, in some direction it's tau, j tau, so it depends upon things, okay, the direction I and j, but it's sz I, sz j. So the action corresponding to this transverse field Ising model, the quantum Ising model that I had written, is this classical Ising model in one higher dimension, okay, with this anisotropic coupling, okay. Okay, so that's all I wanted to cover. So in the next class, we will start with this and show that this is secretly a problem of electromagnetism, okay, and that would give us a different representation of this action. So now that we have derived the action, okay, like really systematically, we would need to write down a dual action or a different representation for this. That's for the next class. Okay, questions?
Yes, sir.
Yeah.
You expanded one of the inner products regarding Sx as e to the power iota pi by 4 something.
Yeah, yeah.
So how did you get that? I didn't get.
I just wrote it down. This is the real answer is that. So you should remind yourself, how did we get this is equal to IPX? Okay. So you started with the commutation relations, right? One way to do this is to start with the commutation relation, write P in the X basis, and solve for this wave function. Okay. You can do the same thing. Okay. For spin-up, it's much easier. You don't have to solve a differential equation. Okay. So the other way is basically, as I sort of motivated this thing that X calculate just for Sx, since you know the explicit wave functions, Sx equal to +1 in terms of Sz plus minus 1 in terms of Sz, you can calculate this thing explicitly. Okay, so that's how I motivated. But if you really want a derivation, you would start with Sx Sz and try to find out the try to take Sx here and Sz here. That's how you did for this, right? And then try to see what this leads to. Okay, it should lead this to the same function that I wrote down. Okay. More questions? Yeah. So let's think about this set of summation. Okay. So for every tau, okay, there is this action. Okay. So then if you think about so for tau equal to 1, there is this, into for tau equal to 2, there is this. But so this product structure, when I exponentiate, it becomes this sum. I'd urge you to open these summations and write them out. Okay. Yeah. So all the sums are product, right? Remember that came from the fact that I had this e to the power beta h, and I resolved. So there was a product in tau. Okay. So that resulted in the products of the sum when I use the resolution of identities. Okay, lunch. Any more questions? Okay, so so we meet eighth on eighth here. Okay.